Okay, welcome back. Happy Monday, everybody. Just handed back test number 2. Today we are doing our first day on algebraic fractions. Next time is our second day, and Friday is our third day. So this week is all about algebraic fractions. Coming up Monday is our last day of new stuff. That is going to be equations involving algebraic fractions. So this is our last themed topic of the course, is algebraic fractions. Wednesday next week is our fifth and final quest, only on this new stuff here. And then we've got 2 review days before the final exam, which will be here before you know it. Any questions on the calendar? Okay, here we are on 224. In this lesson, we begin our work with algebraic fractions, also known as rational expressions, including simplifying them, multiplying them, and dividing them. We're going to go kind of quick here because this is sort of a long demo, but let's jump in. Here are some examples of algebraic fractions. All of those things are fractions clearly, but what makes them algebraic fractions as opposed to like ordinary fractions is that they include variables, right? It's not just number over number, it's fractions involving variables. And so that's why we call them algebraic fractions. Okay, so it turns out we can do lots of things with algebraic fractions in the same way that we can do things with ordinary fractions involving numbers. So we are going to evaluate, simplify, and perform operations. So first, a quick review of how we reduce. Suppose we look at the fraction 24 over 54 and we say, hey, let's reduce that. So the way we reduce it is to look for the biggest number that goes into both top and bottom, yeah? What is the biggest number that goes into both top and bottom? Clearly 2 goes into both of them, right? They're both even. Anything bigger than 2 go into both of them? Yeah, it turns out 6 goes into both of them. And so you reduce both top and bottom by 6. But what does that really mean? We're going to look at this one in like slow motion to really see what we are doing when we say reduce top and bottom by 6. 24 is equal to 6 times 4, agree? 54 is equal to 6 times 9, agree? Okay. How do you multiply 2 fractions? You go straight across. So would you agree that these 2 things are equal to each other? Typically, you start with the 2 fractions multiplied, that's the right-hand side, and then you multiply them across, and that's what's on the left-hand side. So in some sense, this is going like the weird opposite direction from how you normally go, but you should buy that they're equal because you just multiply straight across, yes? Okay, and now that I have this fraction 6 over 6, well, what does that equal to, really? 6 divided by 6 is really the number 1, right? And so I'm not going to say cancel it, I'm just going to say rewrite it as 1, and then 1 times any number is just that number. And so we get 4 over 9. But that's, of course, you know, like what you would have gotten. You would have just canceled the 24 and 54 and said, oh, how many times does 6 go into each? But I really want to be clear that what we are doing here is rewriting 6 over 6 as 1 and recognizing that the 6's being there is the same as nothing being there because a 6 on top and a 6 on the bottom just gives you a 1. So we can cross off the 6's because 6 over 6 is just a fancy form of 1. We're going to see lots of fancy forms of 1 in this incoming classes. So we're going to abbreviate that FFOO, which is really hard to say, so we're going to make up some kind of nonsensical pronunciation of this so that we can actually say it. Fufu is what we're going to call it, okay? Fufu, fancy form of 1. Let's take a look at this example here, number 4. Are we allowed to cancel the 2's in these fractions? So the first one involves multiplication, 13 times 2 over 2 times 3. The second one is addition, 13 plus 2 over 2 plus 3. And the last one is subtraction, 13 minus 2 over 2 minus 3, okay? In each of these cases, we've got 13's and 2's in exactly the same spots. The only thing changing is the operation. So let's see in which of these cases we're allowed to cancel. Okay, 13 times 2. What happened here? Done. 13 times 2 is 26. 2 times 3 is 6. If you reduce both of them by 2, what do you get? 13 over 3, yeah? So were we allowed to cancel those 2's in the beginning? Yeah. In fact, that would have saved us some time if we had just said, oh, 2 on the top, 2 on the bottom. They both become just a 1, and you get 13 over 3, which is the right answer. Okay, so apparently we are allowed to cancel when we have multiplication on top and multiplication on the bottom and exactly the same number on top and bottom. All right, that's what we've established. Okay, let's try over here. 13 plus 2, that's 15, divided by 2 plus 3, that's 5. So I guess that works out to 3. Clearly, that is the right answer. Now let's ask ourselves if we get the right answer when we cancel the 2's. So if you cancel the 2's, I don't know, maybe you're going to say it's 13 over 3. Is that the right answer? No. Okay, well, what if you say, well, I'm canceling the 2's, but I have to replace them with a 1. Now what is it? 14 over 4. Is that the right answer? No, neither of those is the right answer. So what we just figured out is that under no circumstances can you cancel when it's addition on top and bottom. Those 2's look like maybe we can get rid of them. We cannot. Addition, no good. Let's try subtraction. Upstairs, 13 minus 2, that's 11. Downstairs is a -1. So the right answer is -11. So we're going to try to cancel those 2's. And if we get -11, then it works. And if we get anything other than -11, then we're not allowed to cancel the 2's. So let's cancel the 2's and see what falls out. So if I just plain cross them off and I guess like replace them with 0, do I get the right answer? No. We got 13 over, I don't know, -3, I guess, which is definitely not the right answer. If I change them both to, like I'm crossing them off and putting 1's, do I get the right answer now? 13 minus 1, that's 12 over -2. That's not the right answer either. So you can't cancel in subtraction. So these examples are supposed to convince you for sure that you are allowed to cancel when you have multiplication on top and bottom. That's the first example. But you are not allowed to cancel when you have addition, and you are not allowed to cancel when you have subtraction. That's really important for us. Even though it maybe looks like we should be able to get rid of the 2's, and we should be able to get rid of the 2's, it just doesn't work. The arithmetic does not work. So that is not a property, even if it's tempting. Okay, so let's take a look down here and start playing around with this algebraic fraction. X squared minus 9 over x squared plus 6x plus 9. The goal is to simplify this fraction, make it look nicer. And so there's lots of things that are exactly the same on top and bottom. Name something that's a carbon copy upstairs and downstairs. X squared. So I'm very tempted to just say, let's cancel the x squareds. Are we allowed to cancel the x squareds? No, because there's addition and subtraction floating around. Either one of those makes this not work. What else is exactly the same? 9. So I say, all right, great, I can cancel the 9. Can I cancel the 9? No, I cannot, because it is addition and it is subtraction. So you might be saying, well, then I can't do anything because it's addition and subtraction, and right away canceling is out the window. Well, that's true in this form, but we're going to write these things, top and bottom, in a separate form. We're going to factor top and bottom independently. X squared minus 9. Let's go back to all the factoring. We saw it on the test and on the last quiz. X squared minus 9. We'll go through our 3 techniques for factoring: greatest common factor, difference of 2 squares, box, in that order. Greatest common factor for the top. What is it? Is there anything that goes into x squared and 9? Just 1. That's not helpful. Difference of 2 squares. Is it? It is a difference of 2 squares, right? It's 2 terms, subtraction, and both of them are perfect squares. So let's do our difference of 2 squares formula. X squared, okay, clearly that came from x and x. Where does the 9 come from? 3 and 3. And what about the signs? 1 plus, 1 minus in any order, okay? So upstairs, I'll just put up here a reminder, that is dots. Downstairs. Now we'll run through the same process in the same order. What's the greatest common factor downstairs? It's 1, which is not helpful. Is it a difference of 2 squares? Nope, it's not even 2 terms. So the only option is box. So it turns out the box method works on this one. I'm going to just write the answer here. We're not going to spend our time doing it, but in the activity you will. But I will tell you that when you use the box, you get x plus 3 times x plus 3. Now, I still see additions and subtractions, which it's still not okay to cancel when you have those. However, addition and subtraction are not the main operations. What is the fundamental operation upstairs? It is multiplication. It is one thing in parentheses times another thing in parentheses. And I don't care what's in the parentheses. That is fundamentally a multiplication on top. And on the bottom, it is fundamentally multiplication. And we've established that you can cancel top and bottom when it's multiplication and you have a carbon copy upstairs and downstairs. What do you have that's exactly the same? X plus 3, and so you are perfectly within your rights to cancel 1x plus 3 from the top and 1 from the bottom. And then we will write our answer here equals x minus 3 upstairs, x plus 3 downstairs. Everybody see it? And then, what can we do? I see x on top and bottom, so cancel those. I see a 3 on top and bottom, so cancel those. Rachel, you're looking like you're not happy. Can we cancel the x's? No. Can we cancel the 3's? No. This is our final answer. So the general process here for simplifying a fraction is to factor the top and to factor the bottom, but the whole point being turn the thing into multiplication. Then look for carbon copies that you can cancel. And it's not enough to know that process. You also have to know when to stop. It is tempting to cancel those x's, and it is tempting to cancel the 3's, and it just isn't possible. So this is our final simplified answer. And I think we'd all agree that the final answer is simpler than the original thing. They're both equal to each other. If you had to play with one of them, you would choose the second one every day. Next page. 3x plus 2 over 6x plus 24. Can I cancel the 3 and the 6? 3 and 6? In its current form, you just cross them off? No. Yeah. Can we cancel the x's? The x is sitting next to addition. We can't, right? Can I cancel 12 and 24? We can't. So the first question we ask ourselves for all of these is, are the numerator and denominator in factored form? And if they are not, then we factor. Again, the process, greatest common factor, dots, box. What is the greatest common factor upstairs? 3. And so we factor that 3 out. And I'm left with x plus 4. Greatest common factor downstairs, 6. And what are we left with? X plus 4. And now the top and the bottom are fundamentally multiplications, which are cancelable. So what do you see that's exactly the same on top and bottom? X plus 4. So we get rid of those. But then we can actually reduce even more, because even though 3 and 6 are not exactly the same, it's just an ordinary fraction which you can reduce. And what do you get when you reduce? 1/2. And that's our answer. And 1/2 is exactly equal to 3x plus 12 over 6x plus 24. So which one would you rather work with? Well, clearly 1/2. But we don't get there until we factor. Okay. Next one, 2 plus x over 2. Can I cancel the 2's? You cannot cancel the 2's, but actually one of those 2's is ready to be canceled if it only had a partner. Which 2 is cancelable? The bottom one. The bottom one is not near addition or subtraction. The bottom one is just a standalone 2. It's ready to cancel, but the 2 on the top is not, because it's sitting right next to a plus. So next thing we do is factor. Can you factor on the top? Well, let's see. What's the greatest common factor on top? It's 1. There's nothing to do. Is it a difference of 2 squares? Does it look like a box candidate? No, we can't factor the top. The bottom is just sitting there. And if you can't reduce anything, then it is already simplified. So I don't know. I think our abbreviation was like CBS for cannot be simplified. But that one's done. Okay, so that's all we're going to say about simplifying single fractions. Now we're going to come down here and sort of change gears a little bit. It says, consider the algebraic fraction x minus 3 over 3 minus x. Brand new problem here. And we are going to evaluate this fraction for the values of x equals 10 and x equals -2. Let's try x equals 10. So we are replacing all of those x's with 10s. So we get 10 minus 3 over 3 minus 10. So that's a 7 on the top, and how much on the bottom? -7. And what does that reduce to? That's -1. Okay, and now we'll do the same thing, but we're going to evaluate that fraction at x equals -2. So upstairs, -2 minus 3. Downstairs, 3 minus -2. What do we get on top? -5 on the bottom. +5. What does that reduce to? That's also -1. And it turns out there was nothing special about plugging in x equals 10 or x equals -2. You could plug in any number you want to, 57,000, pi over 7, anything you want to, and you're going to get -1 at the end of the day. And so this is a brand new pattern for us to be out on the lookout for. Would you rather deal with x minus 3 over 3 minus x or -1? I'd rather deal with -1. And so anytime we see that pattern, we cancel, but we got to put a -1 in its place. So here's our observation. Any fraction of the form a minus b over b minus a is equal to -1, like x minus 3 over 3 minus x. So here's an example of how we use this fact. All right, this is already written out for us, so we're just going to read here. This is the original problem right here. 64 minus x squared over x squared minus 6x minus 16. So we first of all recognize you cannot cancel like x squareds because there's additions or subtractions. You can't reduce 64 and 16, even though 16 goes into 64. So first we factor. The top is a difference of 2 squares, agree? It is important to make sure we get the order right. That 64 coming first means the 8s have to come first. You can't put x's first. You have to observe the order here. Okay, so 8 minus x, 8 plus x, that's the top. The bottom is a box method. We're going to skip the details, and I will just tell you this is the answer, x plus 2x minus 8 from the box. And then we are looking for things to cancel. Take a look at the two things that are circled. 8 minus x over x minus 8. Do you see that that is this pattern? This is the best way that I can describe it. It's exactly the same thing top and bottom, two terms subtracted, except on one of them, it's swapped. That's it. This is the key. Right? Looking for two things subtracted, but just swapped on one of them. And when you cancel those two things, well, you can't just cross them off and not pay for it because they're not equal to each other. But we saw that that fraction is equal to -1. And so when you cross those two things off, at that exact moment, you put in a times -1. You're replacing the fraction that you crossed off with a -1 because that's what it's equal to. You're welcome to put that -1 on the top or on the bottom or in the front, either way, but just put it in one spot. Don't put it on top and on the bottom because then it'll just disappear. So for me, I just typically put it in the front. Okay, next page says, can we cancel here x plus 5, x minus 1 over x minus 7, 1 plus x? So I see two things that both have an x and a 1. You guys see what the terms, the factors that we're talking about? Two factors that both have an x and a 1. And I say, okay, my pattern is supposed to be this, a minus b over b minus a. So do I have that pattern right there? No. The top part is in the pattern. X minus 1, that's looking good. If the bottom part were going to match the pattern, what should it be? Instead of x minus 1, what should it be? Yeah, it should be 1 minus x, right? This is my thing here with my little like longhorn symbols, right? X minus 1 on top, 1 minus x is the only thing that can partner with that x minus 1. So on the bottom, it's tempting, 1 plus x, but it's not right. The only time we're going to have this pattern is if you have a subtraction or a negative sign in both of the factors. So we can't do anything with this. It is simplified or reduced. Okay, the last topic for today, we talked about simplifying fractions. We talked about our fancy -1 pattern. And the last thing for today is how to multiply and divide algebraic fractions. So first, a review of how we do a division problem for ordinary fractions with just plain numbers, no variables. 4/9 divided by 2 over 27. So we'll cross this off just temporarily. So there's like some technique that you remember from some previous math class. I got two fractions. One of them is getting copied and the other one is changing. Which one gets copied? It's not the bigger one. First or second, which one do you copy? First one. So copy the first one, and then you change that division symbol to what other symbol? Multiplication. And what change do you make to the second fraction? You flip it over, right? Fancy word for flipping a fraction? Reciprocal. Right. So keep the first fraction, division becomes multiplication, flip the second fraction. That's our process, right? Okay, so there it is. 4/9 got copied, division changed to multiplication. 2 over 27 became 27 over 2. Okay, and then we are going to multiply. Now, how do you multiply fractions? You heard it before. It's just straight across. So you could do 4 times 27 over 9 times 2. Totally fine. You're going to have to reduce your answer. My strong recommendation is that before you multiply straight across, even though it's allowed, you reduce here and now. Do you see anything on top that can reduce with something on the bottom? How about the 4 and the 2? They can reduce. Now, some folks are going to be alarmed by taking something from one fraction and reducing it with something from the other fraction, right? At the moment, these are two separate fractions. But you can treat them as the same, right? Because we know that we're going to be multiplying straight across. So there's no two fractions anymore. In my mind, it's one fraction. So it doesn't matter which you pick from, whether it's two things, top and bottom, from the same fraction, or one from one fraction and one from another. Totally fine. So we reduce. 4 and 2 become what numbers? 2 and 1, right? Ordinary. How about 27 and 9? Do they have a common factor? They do. 27 and 9 are both divisible by 9. So what did they become? 3 and 1. That's right. So it's really just a 2 and a 3 on top and a 1 and a 1 on the bottom. In this case, so we just get 6 over 1. In this case, it's not a big deal to not reduce first. You could have just taken the original numbers and multiplied. 4 times 27, that's 108, divided by 9 times 2, that's 18. You reduce them both by 9, actually reduce them both by 18, and eventually you get to 6. But it's going to become more and more in your best interest to do this canceling first as the fractions get more complicated because there will be x's floating around, and you're going to want to reduce as early as possible. Okay, so let's take a look at 11. We are going to multiply 15x to the 9 over times y to the 3 times 2 over 35x to the 4 y to the 10. Okay, when I multiply fractions, I like them both to look like fractions. So what am I introducing here? Is a 1. And so sure, we're going to be multiplying straight across, but I'm a fan of reducing anything that I can ahead of time. So for example, 15 and 35 are both divisible by what? By 5. So let's do that. 15 becomes 3. 35 becomes 7. Okay, so we've reduced there. Let's take a look at our x's. I have x to the 9th on top, and I have x to the 4th on the bottom. And we had a property way back when that told you what to do when you had, I think the letters were like this. What do you do with the powers? We subtract them. That's how we cancel these x's. So let's subtract those powers. So how many x's are left on the top and how many on the bottom? So we get x to the 5th on top. And how about on the bottom? None of them. I'm not going to write anything. If you want to write something, put a 1, like a times 1. But for sure, there's no x's down there. Okay, same game with the y's. I've got y to the 3rd and I've got y to the 10th. I'm still going to subtract, but I'm not going to subtract in the top minus bottom order. I'm going to subtract in the big minus small order. So how many y's are left over when I reduce? 7, and where are they? They're on the bottom, right? That was our shortcut. So we subtract and then put them wherever there were more. That's where they will still be when you cancel. Okay, so there's not that much left over. Let's just write it out. Upstairs, I've got a 3, I've got an x to the 5th, and I've got a 2, and we are multiplying. So we get 6x to the 5th divided by, downstairs I see a 1 and a 7 and a y to the 7th. So that's 7y 7th, and that's it. Okay, let's try part B. This is going to be tougher than part A. First observation, this is two fractions being divided. So I'm going to do our technique from the numbers from right up above. Does the first fraction stay or change? That stays, so we copy it just as it is. And be careful here, because there's 4s and there's y squareds. Just make sure you are cautious when you copy. Division symbol changes to what? Multiplication. Second fraction changes how? Flips. Okay, can I cancel, for example, the y squareds here and here? No, they are near subtraction symbols. Can I cancel the 4s? No, they are near subtraction symbols. Same deal on the second fraction. Subtraction, addition, no good. What you could do is make one fraction where you multiply straight across. And multiplying straight across involves, like FOIL or lobster claw or box method, whatever you do. It's a big old process, and it's totally legit. But if you do that, you're going to paint yourself into a corner, and we don't have the tools to get out of that corner. So we actually don't want to multiply straight across right now, even though we're allowed to. In the same way that I said up here, I don't want to multiply 4 and 27, and I don't want to multiply 9 and 2. I first want to reduce. So whatever you do, you want to get it in a place where you can reduce. And we've discovered that the way to get it into that place is to factor. We got 4 things to factor. So there was factoring on the previous quest. There was factoring on the test you just took. I hope you like factoring because there's factoring still here. So the same process as before, greatest common factor, difference of 2 squares, and then box 4 times. Let's do this quick. This first one right here, greatest common factor is 1. It is a difference of 2 squares, so that's the formula we're going to use. The first things are going to give me 4y squared, but they have to be the same. So that's a 2y and a 2y. The last things have to give me a 1. No choice there. It's got to be 1 and 1. And because it's a difference of 2 squares, 1 plus and 1 minus in either order. Downstairs. Greatest common factor is 1. It is a difference of 2 squares. So let's use that formula. Trying to build a 4, clearly 2 and 2. Trying to build y squared, that's y and y. 1 plus, 1 minus. Hopefully we start to see how common it is to use that difference of 2 squares formula. It's nice because it's quick and it's easy to recognize with a little bit of practice. Okay, second fraction, upstairs. Don't just skip to the difference of 2 squares. What's the first factoring technique every time? Greatest common factor. What is it for the top? It's a y. There's no number you can take out, but you can take out a variable, and you should. So what's left when I factor y out of both terms? It's y minus 2. Downstairs, greatest common factor first. What is it? 2. And we're left with a 2y plus 1. And there's nothing else to do. So we factored 4 times. Now everything is multiplication, and we are going to cancel any carbon copies we find on top and bottom. So what do you see is the same? Two y plus 1. Get rid of that one and that one. What else is the same? Is anything else the same? I don't see anything else that's the same, but there is one other pattern we're looking for where we can simplify the fraction, and that was this, or I guess on the bottom, a minus b over b minus a. Do you see it? We've got it in this case. What is it on top? Y minus 2, and on the bottom, the partner is 2 minus y. And so we cancel them, but at that same moment, you're going to put a negative 1 in the front of the entire fraction. So you cross them off, but you replace them with a negative 1. Don't replace both. Either put a negative 1 on the top, like you could decide I'm just going to put a times negative 1 up here and call it done, or you can put a negative 1 on the bottom times negative 1 there, or my preference is to just put the negative 1 in front every time. And so then we'll write our final answer equals, so we've got our negative in the front. I'm not even going to write the 1 anymore. We're going to write one single fraction. Upstairs, I see a 2y minus 1, and I see a y. And we know we're multiplying straight across for multiplication of fractions. Downstairs is a 2 plus y, and also a 2. And again, that's just multiplying straight across. You are welcome to distribute to get rid of those parentheses. You are never obligated to do so. When you have a single fraction, factored form is totally fine, top and bottom. Just leave it as it is. It's full credit. Okay, so then this last piece for the demo is about multiplying and dividing fractions. Whereas all the problems before this involved a single fraction, these problems involve 2 or maybe 3 fractions. And so multiplication, we're going straight across. However, cancel first. In division, you turn it into multiplication by flipping the second fraction, and again, cancel first, which often means a lot of factoring. Okay, go ahead and move on to the next page. I will walk around.